so specifically privacy when dealing with data and when doing data mining and so forth. And so there kind of be three things we'll plan to talk about today. So one part is going to be a kind of a history lesson. So kind of there's been various approaches to try and define what it means to have privacy when how privacy interacts with data. And so these approaches, they're kind of some attempts to define it, which serve some needs, but also have had some shortcomings. And so, I think it's very illustrative to understand what is the state of the art of what is privacy in data mining by going through so some of the history. So some of this will be some definitions, and some of this are going to be some stories. So I'll tell some stories. So the other part is we'll talk about a approach. We'll talk about an approach called differential privacy. It's not really an approach. I mean, you could refer to it as an approach, but it's actually a definition of privacy. And then there are these approaches that go along with it, that if you satisfy this definition, it has some actual formal, strong guarantees. Things that I think are very reasonable, things you should be striving for. And we'll talk about those and the challenges of actually achieving this. And maybe I'll tell some stories here as well. But there's kind of, when this first came out, people said, this is just a theoretical thing, it will never work. And now it's becoming used inside of big companies now, but there's still some weird views of it in the public. And I've linked to kind of a blog post kind of talking about these issues. And then the third point, which we'll actually talk about first, but I hope will we'll talk about first, but we'll carry over as we talk about the rest of things, is the idea of the ethics and the ethics and the empathy that you should have in mind when you're working as a data scientist, or you're doing some data mining. So to kind of give two parts of perspective on this. One is what we kind of, when you started this program on doing kind of understanding big data and doing data mining at Utah, there was actually some pushback from various people at the university, because they're like, okay, all you're doing is NSA is building this big this big data center in Utah, and that's associated with spying on Americans in various ways. And I'm not going to get into the actual ethics of that particular instance. We'll talk in the abstract. But as one of the things we promised to do in the core courses was to talk about the ethical issues with these. And so I had the version of this lecture in the class, already, but I think it's important to keep in mind that when you're dealing with data, there are certain situations that arise. And so if you're dealing with data inside biology, there are a lot of kind of checklists you have to go through to ensure that you can actually use patient data. How are you using it? And there's a lot of care that goes into it. Data mining is much more like the Wild West, right? There are these new views on what it means to be private and what it's ethical to do with people's data. And that's still very quickly evolving, so we don't really have fixed standards. And so part of today will be talking about what does it mean to be private, right? And how to think about that. But the point of this topic that I want to convey is that when you're dealing with data, often your goal is to kind of classify or to group people into categories or to build a model. And so if you're an internet company and you're trying to sell ads to a particular person, you want to understand their profile, and so you're profiling them, right? Now, profiling in some contexts is a word which is a bad word, right? Profiling in the internet context, that's how you make money. That's why internet advertising is more effective than advertising on cable TV or on broadcast TV, because you know who your clientele is, so you can target it more. And sometimes this is a good thing, sometimes this has led to some issues. In other cases, people give you some data, maybe accidentally, and they may not realize it, and it can lead to some uncomfortable situations when they realize that information is not just their own anymore. Okay, so I think the point of this is that the way you should approach it when you're dealing with data, especially data that deals with actual people involved, right, is to kind of think, if you were the data point, okay? So kind of keep in mind that if you were the data point, would you be okay with your data being used that way, to categorize you, or to kind of have some downstream process be run on your data point? If you'd be okay with that, it's probably okay, right? But it's important to put yourself in those shoes. And this is not always easy. What is okay has been changing, right? So Facebook has kind of pushed the boundaries of this much faster than other places had. And this has kind of cooled down the last few years, but every so often they advance some new features which uses your data to give you cool information, but sometimes gives too much information. Like at some point they had a thing where if you bought something, it would automatically post in your feed, right? For various sort of products. And one example I heard was someone had bought an engagement ring on like Blue Nile, which is this website where you buy engagement rings, and it automatically posted on the Facebook feed. So his future fiance found out about it then instead of when he actually proposed, which I'm not sure when that happened. So there's sometimes the information can get out faster than you would want, and you should be careful about these things when you're working with this data. Okay, so when you're thinking about empathy, though, so empathy is kind of, I think there's kind of one way I like to describe this, instead of trying to kind of personally describe it, is to show a video, and maybe some of you have seen this before. But I'll just show about a minute of this clip of, so this is Louis C.K., a comedian, being interviewed on Conan, and there are bad words, but they're bleeped out. So just, let's watch this and we'll think about what it means to be empathy and what it means to be a data point. Oh, hold on. Sound. Okay, I figured out there's sound that works in this room. Okay, let's see if this works.
The terrible thing. So my kid has, yeah, let your kid go and be a better example.
Can you hear this?
Yeah,
is it broadcasting on the speakers?
Yeah.
Okay.
The terrible thing. So my kid has, yeah, let your kid go and be a better example to the kids. Just because the other stupid kids have phones doesn't mean that, okay, well, my kid has to be stupid, otherwise she'll feel weird. Right? I think these things are toxic, especially for kids. It's just this thing is bad, and they don't look at people when they talk to them. They don't build empathy. Kids are mean, and it's because they're trying it out.
Right, so if you're interested, I linked to it off the webpage. You can watch the rest of the clip. It's funny and crude, and everything that's great about that sort of comedy. But the key thing here is I think he described, and very interactively described, what you should think of when you're thinking of empathy, is that you shouldn't just do something and not realize the consequences, right? You have to, when you do something, you should think of how is this influencing the people it's affecting, right? And that's empathy, is to kind of understand this. And so when you're dealing with people's data, you should try and keep these sorts of things in mind, right? So, okay. So I'm hoping, and so, it's hard to give a lecture on like the ethics of stuff, because I can't tell you what is your own personal ethics. I can't, that's up to you, but I can kind of say, don't do something you think is yourself fair. Okay, so now the rest of what I can do is I can tell you what are some possible consequences, so you can, when you think about if you were the data point, what could this possibly mean? What could these impacts have? And then how can you do data mining while not having these issues be a consequence in various ways? Okay. Okay, so let's talk about the history of privacy a little bit. And so, right, so I think the good place to start is that, or a good place to think about this is, as I mentioned, this is especially an issue in like dealing with medical data or personal data related to, that's related to disease. And so, so as an example, so if you're dealing with health records, these can be very sensitive. And so here's kind of an example why. So let's say that you're like the lead person in a company, you're the CEO or the CTO of a company, and you're going up for funding, or you have a publicly available stock, and so your personal status affects the company, right? So, or it affects your personal life, right? But some way, if you're, I usually often try and think most times people don't care about if I did something, if something weird happened to me, like no one's going to care so much. I guess, being a professor, you can make fun of me while I'm writing on the board or something, right? But for certain people, this, people are going to look into their own personal health records. If you're involved in a company, this can affect the stock of the company and everyone that employs, right? So say that there was some study that a hospital, when you came in, so that there was some, so a hospital, it released a data set that said of all the patients that came in, it just had their zip code, and if the patient had cancer or no cancer, okay? And it just had these lines in a table of the data, right? And so now and so it's figured, okay, everyone is set in their own zip code. So there's a lot of people in each zip code. We shouldn't be able to get any information out of this. Should be safe to release this information. But if someone knew that the only person from that zip code who went to the hospital, because it was very big houses, not too many people in the zip code, or there were not a lot of people who went to this faraway hospital, you might be able to identify, say, the CEO of some company who went to this hospital, and maybe they had some treatable form of cancer, but it showed up as they have cancer, this leaks to the media, the stock plummets, right? So you could imagine some situation where releasing this data, you can connect it to an individual, and this can spread information. And maybe this is useful information to have, maybe it's private information, they shouldn't have any the public shouldn't really have any business doing this. Maybe it's partial information, and so it implies something that's not there, right? So kind of a story like this actually happened, not exactly with the CEO, but so here's one story. So in 2000, so the state of Massachusetts decided, in the effort of science to try and gain insight into various diseases and other things, they would release the medical records of all of the state employees. So they the medical records of all state employees. But they said, well, you know, we don't want to give out their names, right? So we're not going to give out the names. So instead, they didn't give out the names. They wiped the IDs, but they kept the zip code. They kept the so the birthday and they kept the gender. Okay. So this was declared like this was going to be safe. You just have the zip code, the birthday, and the gender of the person. Okay, the zip codes are pretty big. The gender kind of is half the population, so still all the males or females in the zip code, or you know, it doesn't zero down too much. So this was 2000, so gender I think was probably only thing the record was male or female at that point. So they thought this was safe, and probably by itself, you probably would have a hard time identifying any given person, even though the birthday might tell you a lot. But at the same time, there was another way to get information from the state of Massachusetts. You can buy you can buy voter data. So this is who has voted, and so this who has voted in the state doesn't tell you who they voted for, but who they voted, and this is used in political targeting and advertising a lot. And so this was only for so for $20 you would get all the voter data in the state, and this included names of people, so the birthday, the zip code, and yeah, so just the names, the birthday, and the zip code of all these people. Okay, and so for the names, you can probably interpret the gender with pretty high confidence. Okay, so just the first data by itself seemed pretty anonymized, but when you have this other data, well, now if you can find the same zip code and the same birthday, then you might be able to line up with the name. And if this was a wealthy zip code and they're a government employee, well, there may not be a lot of government employees in the wealthy zip code, only the kind of the upper echelon, the higher ranks of people. And so what happened was, so there was a grad student, so her name was LaTanya Sweeney, and so what she did is she took the first data set and then she bought the second data set for $20, and she identified the governor. So she ID'd so she ID'd the governor of Massachusetts, and so the story goes, I don't know if there's confirmation of this, but she actually mailed him a packet with all of his health records. Right? She figured out his address and she mailed mailed the, the health record. So she, to his house, right? So he got a packet with his own health records from some anonymous grad student, or maybe not anonymous, but some grad student. This must have said, maybe I shouldn't have released all of the state, employees, all their medical records. So now, I don't know if there's anything worth worrying about in his medical records, but for other people, this may have been, right? So, and so now, the one moral of the story is that now LaTanya Sweeney teaches at Harvard. So she's kind of made a career of kind of identifying these sorts of issues in privacy. Yes?
Just out of curiosity, was she CS or ethics or law?
I believe she was CS initially. Now she works, I think it's related to the medical side of things as well. I don't know her. It's kind of, Harvard has all these weird different positions for faculty. I don't believe it's in the CS department now, but she was a CS grad student, I'm pretty sure. Yeah. And so this was great for her for discovering this, but this kind of kicked off the area of studying privacy and computer science with data. There was some papers that came out of this, and then this was kind of, people realized, we have to be more careful. Up until this point, a lot of companies were very willing in sharing of their data, and things were going well, and now it's much harder to get data from these, not just health records, but also from companies like Google and Facebook and so forth. One reason is because of the privacy issues. The other is they actually turn this data into profit, and if they share it, then their competitors can use the data. That's part of their advantage of the company. Right? Facebook is profitable because they have all this personalized data about their users, and they can target ads towards them. And so that is why they're such a highly valued company. Okay, so this is kind of one instance where you thought something was private, but you can add other data, and it became not so private. Okay, so one of the first approaches that came out after this to say, okay, this is a problem. We can't just release data anymore, but we need to be more careful about it. We need to have some sort of standards, and so one of the first approaches that came afterward was called k-anonymity. And so the idea is that if you release some health records, so you have to remove some information, right? Massachusetts thought just going down to zip code, birthday, and the gender was enough to hide identities of people. But instead of that, you want to kind of make sure that there are certain properties, and this will depend on some parameter k in this case. And in this case, it was that so if you have the so the public data, so every part of the public data that it matches must have at most k identical records, right? So the public data must narrow down to I guess at least k people. So there must be k or more people that have the same public part of the record. So for some parameter k. And often I see values like 4 and 10. So for instance, when I get feedback from the teaching evaluations, so I hope all of you give me kind of good scores and all that. But when I get feedback, I've taught some smaller classes too, and if fewer than 4 people respond, I don't get to see anything. Because I should be able to somehow, I might be able to identify, just guessing on which, if 3 responded if 2 responded positively and 1 was like really mean and said some nasty things, then I could probably figure out who that was and maybe take some retribution. I wouldn't do that. You know, but still give me good scores, right? So the point is, so in this case, at least 4 people, k equals 4, should have responded in order for me to see the records. And this was basically, there's no public data. There's no information about this, about who type of responded, other than they were in the same class. They were in the class, right? So there's some sort of standards when releasing data with medical records, and I've looked at these in the past. I don't have them in front of me, and there are various things you have to do to safely release them. If you're like to work with to get funding from NIH, you have to follow certain standards, and one of them has to do with the pattern that looks kind of like this, where there's some restriction on you can't de-anonymize up to a certain number of people. So this was k-anonymity for a while. There's a lot of work in trying to figure out how much public data could you release while still preserving this property. Okay? So what is, as I've mentioned, this is not going to be the end of the story. So what could go wrong here?
You got nothing to release?
Yeah, so one issue, and this won't be the, so nothing to release. So if I got my teaching scores back and only 3 people replied, or the K was 100, and so I didn't get to see anything, and no one got to see anything, then I wouldn't have anything useful. Yeah, so if you set K to be too high, then you don't get any data. Yeah, so there's always this push-pull between the amount of data you can get and the amount of privacy you preserve. Yeah.
And if all the data points are the same in a certain partition, for example, zip code, then you can say something definitively about all people in that zip code.
Yeah, that's right. Good. So just repeat that. So if you narrowed it down to a group of K people based on the public data, but all of these people had cancer, right? Then you still know that anyone who fit that description in the survey also had cancer. Right, so you might narrow down to a group of people. You may not be able to identify personal medical records, but you may be able to say some trait that came with that was true to everyone in that group. Right, and so you would still identify certain private properties of them that you wouldn't want to share. Right, so one approach. So this was then realized after maybe some thought, or eventually it was a few years, I think, but before. And so then there was another standard that came out that was called L diversity. Okay, and so this is the same. So it satisfies so k-anonymity. So it has this. Plus, after this, it says that inside of each group of K people, there have to be, for any private trait, it has to fall into L classes. And maybe L is 2, right? Cancer and no cancer would be fine, right? So, at least L distinct, so private traits. Right. So again, if you had 10 people in the study, there at least has to be one person who does not have cancer and one person with cancer. Right. Maybe it doesn't matter if they all don't have cancer, but you kind of say you want at least one of each of the private traits, or at least 2 of each category in the private thing. You want each of those to be present.
But how do you break this up? So how you partition this is going to make a difference on the diversity. For example, say you're not paying attention to zip codes.
Yeah.
And you're paying attention to state level or something like that, right?
Right.
And I mean, the whole point of data mining is to find these trends in the data.
Yeah.
And you almost have to know every question to ask in order to be able to ensure that this is true. Yeah.
Yeah, that's true. So, yeah, so it's harder to satisfy this, and so the definition depends on what are considered the private traits. And so that makes it up for interpretation. What may seem like a harmless private trait might end up being something down the road that is, you can connect to something else. Maybe, you know, if you put a lot of, you know, if you put a lot of gel in your hair or something, so you wear like a mohawk or whatever, maybe now this seems harmless, or maybe not, right? But maybe that was highly correlated with getting cancer of the scalp. So later, 10 years later, everyone knew if you did that, well, then you probably have cancer now, right? You know, these sorts of things. So you don't know these ahead of time, which makes it difficult. What is private? What do you need to protect, and what don't you? Yeah. So again, these are issues that, you know, are not that we don't know how to solve. Yeah. There's kind of, I mean, and this is still, and there are some issues like what you said with this, where, you know, these traits later can be identified with, you know, if everyone has a certain property, maybe you don't know that is bad now, but maybe it can be connected to something that's bad later. Right, and maybe it's with another data set, right? Maybe it's with this, there's another data set that connects these sorts of things and it helps you identify a person in that way, right? So that can also be bad. Like there's only one person who bought that much hair gel in the States, then you know who that is, right? Okay, so this, because of issues like this and similar, let's see if, yeah, so there's, because of issues like this, and I think that kind of nails the main problems with this. There's a third category of standard, and you see the kind of theme in these names that was called T-closeness. Okay, so it could be that everyone in the zip code, they had different patterns of some things, but they were very far from the norm of the general population. So you kind of could get some sense of the pattern of those people, right? You suspect that this may be an issue later on. You may not be able to connect it. You may be able to identify that, say, you know, maybe people were much more predictive of whether they were voted, like if they voted either, if they voted Democratic or Republican. So maybe in like parts of the avenues, there were some people who voted Republican every time, but didn't want their neighbors to know, because everyone else is like, oh no, you know, they're talking about that. So, but if they're identified as being Republican there, they might get ostracized by their, you know, by their neighbors, and that may not necessarily be a good thing or bad thing, but it may have consequences. If you could say everyone in this one block voted a certain way, that would be. Or maybe not specifically, they voted different ways on different races, but in general had this general view, then the neighboring people may kind of ostracize that block. Who knows? So there's this third category called T-closeness, and what this, this again is going to start with the one above. It starts with the L diversity, but then it has another property on top of that. So that it has L diversity, which means it had the key anonymity. But then on top of that, it said that the distribution of the private traits is close So, and there's some parameter t that tells you how close it is. So t close, and it's usually measured in the Earth mover's distance, which is a distance between distributions that I think I mentioned in the distance part of the notes, but we didn't cover it in class. But it's the distance between these distributions. So it has to be t close to the entire data. Okay, so every segment of the population has to look in private traits similar to the full data set. So you don't even know that this area has a certain pattern. Okay, so now hopefully this protects against these things, and t is some parameter of how close it has to be, and that's set based on whatever you want that to be. Now, getting back to the first objection, maybe you have something to release. Maybe there's a way to break the data up into these ways, into these parts. But maybe instead of nothing to release, there's another problem. Is there's nothing to mine, right? So if every population part of the data looks like the whole data set, you're going to have trouble finding meaningful patterns in this now, right? So now we're kind of, maybe it's some direction in one way, and you can pick out some correlation if t is large enough, so it gives you enough slack. But what's happening is you're this trade-off between the privacy and the usefulness, and the more constraints in this way you push, the less useful the data is, and then it's harder to actually figure out what is the most information you can release that satisfies all these conditions. And this kind of, so what kind of happened is the community kept creating these standards which seemed more and more safe, and people followed them less and less because they were either harder to figure out how to satisfy these properties, or the data was useless once it was released. Now there's still some cases that people have shown you can satisfy some of these, and you can even t-closeness and still find some patterns, useful patterns in the data. But it just this kind of worked itself into a draw, right, between the release of data and the usefulness of it, to the point where less and less data has been released of this form. It's harder to find data. A few of you have special IRBs or some access to specialized data, and that allows you to look at it with some promise that you're not going to release certain information, right? And I don't know if anyone this year made me sign a non-disclosure agreement. In past years, people have worked for companies. I've signed non-disclosure agreements that I'm not going to say anything about the data, and I let them work with the data their company has, right? So the companies internally can do this and kind of not be so worried about it, but but externally, if you wanted to do something fun with the data, it might be harder to get. Or an academic setting, which kind of affects what I want to do, it becomes harder to develop new techniques because I don't have access to data of a certain scale. So this is kind of, I guess to summarize this, let me talk about a couple of concrete examples. Like another issue with this whole line of work is that it kind of assumes that there are these public traits which you can prove properties, and private traits which you say, this is all the data out there. We can prove properties about the security of this, about these traits. And that's all the data, right? But in reality, just like in this example with the Massachusetts health records, there could be other data out there that you can use to line up with this data and learn something more about it. For instance, and I'll use this, start with this example. So how many people know how tall is Sylvester Stallone? Yeah?
I'm cheating, I read the notes.
Okay. Okay, so there's some good reason to believe that When he was a young man, like the Rocky movies, he was 5'8", right? So let's say he's so Sly Stallone is 5'8", but for various reasons, a lot of Hollywood actors don't want people to know how tall they are. And if you try and look up on the internet about how tall he is, there's lots of different information about it. There are pictures with him next to other people, and is he wearing platform shoes? Has he had a height inducing surgery that may have happened? I'm not sure. He may or may not be 5'8". But what if information was released that said, it didn't say his height was 5'8", but said that he was the same height as the average man from New Jersey, right? And maybe they got this information, say there was some meet and greet in New Jersey with Sly Stallone, and he shook hands with everyone, and they blurred out the faces of each individual, but you got a picture of him right next to everyone, and he wasn't wearing shoes, right? So you knew it was his true height, right? So then you could say, okay, if you average out all the height of the people he's meeting, he's the same average height. But then you can figure out the height of the average man from New Jersey through a separate survey. Maybe you really care about this issue and you go and you collect this data somehow, right? You can go around and measure people yourself. There's ways to get more data to try and kind of de-anonymize stuff, and like this happens. Okay, so another example of this is so the Netflix challenge. So who heard of the Netflix challenge in 2006? There's a great data set still out there about this. So in 2006, so Netflix, which was not as big of a company as it is now. It was all over stuff over the mail, but they had these ways you could rate movies that you saw on the computer. Wild, right? And so it had this data set of customers where the D1 data set had had the user ID. It had the identifier of the movie. It had the date of the grade of the movie, and it actually had a grade. And I think this grade was between 1 and 5, right? And so everyone rated a movie between 1 and 5. 5 was the best, 1 was the worst, and so it had this one data set that had this information. They also released another data set, D2, which was user ID, the movie, and the date of the grade, but it did not have the actual grade. Okay, and what they wanted to do was to predict how people will like this other movie that they actually watched. Okay, so they know they watched this, they want you to predict this grade. And they had their own internal algorithm that did a pretty good job, and they use this to recommend other movies to people. If you have Netflix, you can hardly find a movie without going through the recommendation system. This is kind of a core part of how the system works now. And so they had their algorithm, but they said, if we release this to the crowd and promise them if they improve upon our algorithm by something like 10%, we'll give them $1 million. And so this generated a lot of excitement. A lot of groups were working on this. Eventually, the best, I think they got to like 9.8% improvement, but I think they may have given them most if not all the prize money anyways. But it was a group from like AT&T Research and an academic group from Canada, maybe in Waterloo or Toronto. They eventually combined their solutions together. And so there's a lot of academic effort and a lot of people learned about how to do these approaches kind of based on this data set. It was a great data set. And so they kind of gave this, and what you could do is you could use this data to make predictions on D2. You could submit those predictions, and then they would tell you a score of how well you did. And so to give you the score, they never gave away this information. They had a private data set, D3, that they would so they would eventually evaluate. It was the full data here. They had all the data in this case, ID, movie, date, and the grade, but this one was private, and so you would submit. This part was public, and so this part was so they would evaluate. So you would submit a classifier or something, and they would run it on this data set, and they tell you they tell you how well they did, right? And so this was kind of, think of this like this cross-validation. You had this unlabeled data, you have this training data, and you have this evaluation data you want to generalize to. Okay, so there was a lot of cool research that came out of this. This was great. Around 2010, they were planning on doing a follow-up with this, where they would give not just user ID, movie, date of grade, and grade, but some other information as well out about this, with a much larger data set as well. And they were planning to release this. They started to announce it, and then something interesting happened. Can anyone guess what happened? They ended up not doing a second challenge. Why do you think they didn't do a second challenge?
From your notes, someone was able to do a matchup using the original data set from IMDb, I guess? Yeah,
right. So people realized, okay, this data is out there, but there's also this data on IMDb, and so most of you probably just interact with IMDb just to look at it, but there's also, it gets a lot of ratings. Some people go in and rate a lot of the movies that they watch, and IMDb people choose which movies they rate. They have a user ID, and you can maybe connect that to individuals. And so the IMDb has a user ID, it has a rating, and it has a timestamp for all these, and so also has a movie. And you can probably guess that someone who really was into IMDb and liked movies so much that they would go in and rate them on IMDb as well, they would likely be someone who had Netflix, because that's the best way to watch a lot of movies. And they also had this timestamp on the rating. And everyone watches a small subset of all movies, so it turned out it wasn't too hard to identify, using the user ID from IMDb, which users were the same ones in the Netflix data set. But this is the same information, so what's the problem? Is there a problem?
For the challenge there is.
For the challenge. Okay, yeah, so maybe you could identify how they rate them on IMDb, and you could predict this blank one better. Right? So that's, yeah, so that's probably true. But there's also a personal issue. Like, they may not have rated all the same movies in IMDb that they watched in Netflix. Some movies, or maybe this Like some people would watch movies and maybe not put the grade in there, right? They wouldn't. Maybe they rented at a certain date, but they didn't. But they didn't put a grade. Or wait, maybe that's not. Sorry, that's not the issue. So they would rate them and grade them in Netflix. They figured this was anonymous, but there was not much anonymity with IMDb. People would link to put their photo on there. They would say, you know, they would put like where they lived, what their real name was associated with this ID. So you might not rate all the movies you watched in IMDb. If you watched some movies you were embarrassed about, like maybe it was a guilty pleasure, maybe it was some other sort of pleasure. You know, it could be something that you're embarrassed. I guess they don't have that on Netflix, but there could be something you're embarrassed about having watched that you could just avoid by not rating an IMDb, which was much more public. But now Netflix releases this data, you identify these people, and now you see that now people are like, I don't want this data out there, right? Even though similar data was on IMDb, but now there was some part they didn't want people to know that they watched this, right? Maybe there was some, you know, I don't know, there's some like, some weird sport that they really were into and watched a bunch of movies about and they were embarrassed about it. Who knows what could be. But so people sued. People sued Netflix over this because a paper came out showing how to de-anonymize most of the Netflix data, and there was a lawsuit against Netflix. I think the lawsuit was eventually dropped, but they also dropped doing this next challenge, which was unfortunate from a research perspective. Yeah.
Regarding dropping it, was there some sort of legal statement like that in some sense absolved Netflix of the responsibility and that they couldn't foresee this?
I don't think there was something that they couldn't foresee this. If they had been wrong, then I think that's their fault. I don't know if there was some compensation given behind the scenes, or that they can't talk about it, or I don't remember the details of it. But I don't think Netflix would be completely absolved just because they couldn't foresee it. It could have been that it was not considered harmful. It was not considered like there wasn't anything worth suing over, and maybe that's why it was dropped. But there was concern, like the fact that they were being sued was bad publicity and so forth. And other people say, "Oh, I don't want to sign for Netflix because they're just going to release all my data." You know, there's that sort of thing. So I think that was more the issue. I think if you release data and you don't realize it's bad and later it becomes an issue and it leads to damages, I think, you know, there was this case with Gawker and Hulk Hogan, and they claimed, oh, we didn't know this would be that damaging for him or something, but they kind of, I guess they should have clearly known there. But there are these things where if you're negligent, that doesn't absolve you from being in the wrong. And that's a general legal thing, and I think that should carry over to releasing data in that sense. Okay, so that was one thing. Okay, so this is kind of about the bad news. Let's switch gears a little bit. So this is kind of, I mean, this is part of the stalemate now, where not a lot of data is released, and so there's some data set out there. Did any of you look at the data from the SNAP website on Stanford, snap.stanford? They used to have more data up there, especially from, I think from Twitter, and at some point Twitter asked them to not have it public anymore. So they took it down. They have good relationships with, they want to keep good relationships with the companies. So there's been, the amount of data out there has actually has decreased over time. But there's like WikiLeaks and other things that are dumping interesting data sets for better or worse as well. I shouldn't comment on the better or worseness of various things. Okay, so let's switch gears and talk about differential, so privacy. Okay, and so to talk about this, I'll try and this is really a careful definition of what means to be privacy. And so I'll have to get a little bit more into some notation a little bit here. And I find that, I found that this definition itself can be kind of confusing, and there actually has been a lot of confusion about what it means. So let me try and give a fairly precise statement for simple cases and go through some examples. So the idea is that if you have think of two data sets, so D1 and D2. Okay, and so this word differential means like the difference between them, or if you take if you're doing like a mathematical differential sort of thing, it means you're kind of moving from one to the other by a small amount, so something like that. And so what the idea is that you have two data sets that you want to say if these are going to be close, then the statistical analysis on them should be similar. So you want to say similar statistical analysis. Okay. But you also want some privacy property about this. So if you can't, they're going to be so it's something like you can change one data point from D1 to D2, and so this should not affect the statistical analysis. It's kind of what's going on here. So so the privacy talks about the similarity between the two data sets. And in reality, what you should think about this is that there's the truth, and then this is what is public, right? So you see this data set D2, this is public. It somehow came from the truth through some process. There's some process here. And there's some random process. And so it changed some of the data from D1 to D2. But the overall statistical picture, you can still do data mining on D2, and the result should look similar to if you did it on data set D1. And they're close, and in fact, probably some of the data points in it are going to be exactly the same. Okay, so I can't say that if I have both of them, I can't identify certain data points. But just think of it like there might be a non-randomized version of this now, but think of it like a random process. I'm going to pick some random data points and change them, and I don't know which ones those are. So that if one of those data points represents you, you can say, oh no, mine must have been changed. Mine must have been the one that was changed. Okay? It's kind of the argument. So if this D2 is public, you shouldn't say, well, that's data. Maybe you can align it with another data set with actual data points, but the private property that you want to keep private, there's no confidence that that's the true private property. Okay? Okay, so let's get a little bit more specific, and hopefully this will make a little bit more sense. So this is some random, think of some random process converting between. Okay, so think of D1 and D2 are, in this simple example, are going to be these n bits, right? So I've got a string of n bits that are zeros or ones, and so I want to be able to, so let's enforce two things: that the Hamming distance between D1 and D2 is going to be equal to 1, right? So they change it at most 1 bit, right? So they're changing by 1 bit. So this means change 1 bit. And also the property that the probability that some query, and I'll define what this means, is in some range on D1, and the query on D2 is also in this range, in the same range. I want this to be less than, it's often written as e to the power epsilon. So there's some epsilon parameter. And so this x, e to the power epsilon, this looks about like 1 plus epsilon. Okay, it's written this way because the math is easier to work with here. I should think of this as a 1 plus epsilon. So the ratio of the probabilities of being in a certain, having a certain property, being in a certain range, is very close to 1, the ratio of it, right? So that means that this one on data set 1 could be larger. You could reverse this as well and look at the other side, the flip of this, and then you'd have, or you have a 1 minus epsilon. You could also look at those properties as well. But so think of it, if this epsilon is like 1%, then these answers are off by 1%. Okay, and so now if the data set looks like this, what does a query look like? So example of a query could be if you have a data set 1, 0, 1, 1, 0, 0, 1. So if this was D1, and so then a query could be, it's going to be a string 0, 0, 1, 1, 0, 0, 1, 0. And so then you do the XOR of D1 and Q, and you're going to add up the size of this XOR. This could be a query. And so what that's going to give you is it's going to be true if the bits are different, right? If they're the same, so it's going to give you the size of 1, 0, 0, 0, 0, 0, 0, 1, 0. So this is equal to 2, this example. Okay, so this is kind of the first sort of thing people looked at. A more common thing would be, for instance, a query. So that these are certain properties that someone might have. They have colon cancer, they have thyroid cancer, they have breast cancer, they have colon cancer and breast cancer. This is pretty rare, probably. But you know, these are the sort of data sets of an individual person. A bunch of traits that they could have. One is they have the trait, 0 is they don't. And a query is, do they have all of these traits? Something like that. Or maybe it was their age is one of these values, and the query is going to be all the values up to something. So then they're underneath some they're underneath some age threshold. So their age range is in 0 to 10, 10 to 20, 20 to 30, 30 to 40, 40 to 50, and so forth. And then a query could be the first 4, so that they would be under 40. If it's 1, 1, I guess. Yeah. Or it doesn't have to be an XOR. It could also be an AND, for instance. XOR showed up in some other examples I saw when I was putting the notes together. Okay, but so it could be some query like that. So you want to understand just some bits, and you have some way of asking about the number of bits that satisfy some property. Okay, and that's what this looks like. And then R, this range R, could be something like 0 to 3, right? So this could be a range. So if the value of the XOR value is 2, it falls in this range 0 to 3. Okay? So now you want to say for a query, I want to say that the probability it falls in there should be, you know, I want this to be close on D1 and D2. So I want to create a data set D2, which for any query I'm allowed to ask, which has to do with a queue and a range I care about, that these should always be close somehow. Okay, and so if the value was true value was 1, I can change another bit, and I know it always has to be, this value can only be off by 1. Right? If I'm only changing bits, and this somehow has to do with counting the number of bits that satisfy something, changing 1 bit will affect this probability, the size of the query will be off by at most 1. So this is what I have to worry about. And so what you do is you can randomly flip one of the bits, and then if you can only ask queries like this, you could say, well, there's some chance that I'm going to give you back another answer. I'm not going to tell you, I don't get to see the full data set. I only get to ask these queries. And if I can ask these queries, sometimes I'm going to get the answer, yes, it's in this range, or no. And the probability it's going to be to have the same answer is going to be bounded. Okay, I'll go through a couple more examples of this, but before I go through some examples, let me just say, before this gets kind of more confusing, that there are 2 ways of interacting with this data. So one way is interacting. There's the interactive approach, and that's where D2, which is from D1, say plus noise, right? So D2 is private, but you can ask some questions of it. Okay, so think of it like this Netflix challenge, kind of a similar situation where they're holding on to another data set, and I can ask questions. Here's a classifier. How many answers did I get right? Right? And they can only ask 1 question a day, so I can't ask too many questions. The more questions you can ask, essentially the more you can learn about this data set. I can ask something like, given a query, and the query is an AND with a 1 bit here and a 0 bit everywhere else. And I want to know if that value is 1 or not. The range is going to be 1. I can learn the first bit. Right? Now that bit might have been flipped, but I can learn a lot about the data set. I don't want them to learn the data set. So maybe I restrict what sort of questions they can ask. Any query must have a certain number of bits it depends on. Right? I can't ask any query. I can only ask certain types of queries. I restrict the queries they can ask. And one of the good things is that maybe I can have a fixed data set D2 ahead of time, but maybe I don't need a fixed data set D2 ahead of time. I just need to have it be, the answers be internally consistent, and I need to have this property to be satisfied. So I can decide every query what answer I'm going to return based on D1. And if I'm careful about how I answer them, I don't just make up a data set D2 at a time, then I can actually preserve more privacy. And so this gets to be difficult for complex sorts of queries, but for various sorts of queries, you can actually do some pretty cool stuff. You can ask a large number of queries of a certain class of queries and not give away a lot of information about the original data set, and have some data set in D2 that you think you don't really know what it is, but you have constraints on it that must be almost satisfied by each of the queries. So think of those logic puzzles when you're a kid, like Sally, Joe, Bob, and they went to the park, the beach, or whatever, and you have all these clues, and you don't really know, or maybe a more mild thing is like if you're doing like Sudoku, you don't know all of the things, but you're kind of keeping track of constraints. This number must be something or the other. And you don't zero it, you don't narrow it, you don't write it in until you absolutely have to. Right? And you eventually can figure this out. But if there's not enough information, not enough constraints in there, that there may not be a solution, you don't have to constrain yourself to that solution yet. And so it means you can still change your answer of your internal representation of what D2 is based on what answers you've given to the queries. And this gives you actually more leverage in keeping it private with more questions that are allowed to ask. So this is one approach. The second approach is what you might think of is of course the non-interactive approach. And so this is where you actually release the data set D2, but it satisfies the property that for a certain type of queries you're allowed to ask, that it'll satisfy that the distance between them is small. This may not be 1, but it may be something else. The distance between them is small, then that preserves certain statistical properties, and for certain, or it maybe is even large. There's some distance between them, and for any sort of queries, you're going to have this guarantee that you're going to have about the right answer from the true data set. But you actually release the data set. And this might be something where you would do it instead of these discrete values, it might be some sort of continuous value. So let's go back to this example. So the common thing to do here is now think of this data set as a single number, right? So think of this data set D1. Let's say this is the true height of Sly Stallone. Okay, and so let's say that it's in inches and its true height is, let's see, in this example I give is, and let's say the true height is 68 inches. Okay, 68 inches, and I'm going to release another data set that's going to be equal to the D1 data set plus, Laplacian noise. And so we'll write this as Laplace with some parameter epsilon. And so a Laplace distribution looks like a Gaussian distribution, but it is pointy. So it has infinite support, but the expected value is 0 essentially. So the expected value is 0, but the support is infinite. And so if you have, and it essentially it guarantees this, and it kind of guarantees this right property. So so if you wanted to say that, so you added noise to it. So let's say before the noise instead that this was 68. And so let's see, now you have some query range. This is some range that you cared about, and let's say that this is 70 and above. So he's above 510. What's the probability he's above 510 based on releasing this data set? And so let's say that you release the data point at 67. Okay, so he'd be 5.7 instead of 5.8. But you knew he was generated with this Laplacian noise. So you say, was the probability that that D1 is greater than 70? And this is, the distance is going to be 2 here. And so adding Laplacian noise, so the Laplacian, this is equal to, so the exponent of minus epsilon. Right, so a Gaussian distribution would be exponent of minus epsilon squared. It's just minus epsilon. And so if you add this noise to it, you're going to say the probability that this Laplacian is out here, right? So the true answer is 0, but maybe I added noise and it was out here. And so this is going to be, as far as I know, I added Laplacian noise, minus 2 epsilon. Because it was a distance 2 times this epsilon. This is the property that has that the integral of this part of the distribution is going to be the exponent of minus 2 epsilon. So e to the minus 2 epsilon. And if which is going to be approximately, so it's going to be approximately 1 minus epsilon, I guess. Oh no, it's going to be small. Okay, but the ratio is what's going to matter. And so, and in D2, so this, remember this was 68, this was 67. So this was greater than 70, right? This was going to be X. So if this is what I saw, then the probability, I knew that this was given Laplacian noise. So let's say I saw this 67, and I assume it came from something with Laplacian noise. So the probability that the true value was actually here, because there's symmetry, I could have said the true value was 70 or above, then the probability that the true value is here and I generated Laplacian noise and got this data point, as opposed to starting at 68, that's going to be the exponential of minus 3 epsilon. And so if I take the ratio of these, the ratio of D1 greater than 70, probability D2 greater or equal than 70, then this is going to be right, the ratio of these two things, which is going to be exactly the exponential of epsilon, which is what we want. So if I set epsilon right here, so in this case epsilon is going to be equal to 1 in this case, then I'm going to get or no, it doesn't have to be equal to 1. Whatever I announced I'm releasing it with this much air, and so if it looks like this sort of distribution, then the ratio of the two things depend on the of the two things. If they are off by 1, is only 1 plus epsilon. Okay, so this is roughly how the underlying math works. If you release it with this Laplacian noise, you get this guarantee that the probabilities of them satisfying certain events have a bounded ratio. And so you can release simple data this way, and then there's some ways you can turn this, get similar properties that are harder to write down for complex, more complex, say, higher dimensional or multi-point sorts of data. And people have worked that out as well. Okay. Yeah.
So this adds, in some sense, to the variance in the data, correct?
Correct, yeah.
So if you want to do inference on that, would you maybe release epsilon so that you could release the variance back?
Yeah, so you want to release epsilon. You can't get the variance back, it's been added in, right? But you can then model it properly, right? So you can build a proper, you can build that into your inference. Yeah. Okay, so there's one more example in the notes where I did a little bit better job of this interactive approach with the bits. But I think I'll just stop here and say kind of some general words about this. So kind of the main thing you should get away from this is that if you follow these properties and if you come up with the right algorithm, you should be able to release some data while still preserving some properties. The more accurate those properties are, the less private the data is. Right? If I want to preserve these properties, so for any query this ratio is 1%, well then I'm going to be pretty sure that what I released is going to be very close to the true data set. Right? If this property, if I had a much larger variance in my Laplacian noise, say I'm willing to have like this to be 30%, then I know that the variance of this data set is much more, and I know much less about, there's much more privacy about this data point that has been released. I know much less about what that actual value is. Okay, and so there's this trade-off between privacy and information. So it turns out people have, like, these are kind of the very basic approaches here. If you want to show you can preserve certain statistical properties about something, it better be some sort of statistic that is not very affected by changing one data point or by adding noise to all the data points. Right? So if your statistic is robust to this sort of noise, then it should be fine. Right? If those types of noise we talked about on Wednesday, if your statistic, if your approach is going to be robust, then you should be able to add noise and you've obfuscated the data to some degree. Because you may be able to get rough values, but not the exact values. But you should need the exact values to get the general pattern in the data. On the other hand, if your data is very susceptible to one outlier, or if you change, or if your analysis technique is very susceptible to one outlier or by changing the data just a little bit, then differential privacy is not going to work well. You're going to lose that sort of prediction, but you probably shouldn't have trusted that prediction in the first place because it wasn't robust to actual measurement sort of noise. Right? So this sort of approach should work. And so people are figuring out ways that you can kind of generalize these properties beyond a single value and ensure that that all of this goes through. You can do things more powerfully in this interactive approach, but then there's this computational bottleneck where you actually don't want to have fixed this data set D2, otherwise you just would have released this. If you can allow some interaction, you can do better, but then there's some computational issues. Okay, so this differential privacy itself is a definition. If you satisfy this definition, then you preserve it up to those properties. You don't know any particular data point up to the the sort of kind of probability of queries up to like this sort of property here, where probability of query is going to be a ratio of these. This is what you can guarantee. And so the question is, how much information can you still get out of D2 while having this guarantee for some value of epsilon? But this seems like something you should be able to trust. It doesn't say it should be, even if you add in more data, you don't know that the data in here was actually correct. So it should be much more secure. But making this general and accessible is still kind of a work in progress. But hopefully over the next 5 or 10 years, this will be something that will become more, I think maybe more standard and widespread. Okay, great. We'll start talking about graphs and starting by Markov chains on Wednesday. That'll be the last general section of class.